Hello everyone, I'm going to present an intrinsic and extrinsic defect study of magnesium tetraborate through a computational atomistic modeling. This work is a collaboration of Federal University of Sergipe, Federal Institute of Sergipe, Pisa University and Keele University. This presentation is divided in motivation, where we will talk about the why magnesium tetraborate doped with lanthanides is important for dosimetry area, pointing out some open questions about this material. After we will present the aims. In the methodology, we will explain the classical atomistic modeling applied, giving a short discussion about the potentials used to describe this material. In results, we show the calculations for intrinsic and extrinsic defects, comparing with some experimental results and the conclusions of the work. The first motivation is that magnesium tetraborate or MbO doped with lanthanides can become a new TL and OSL standard dosimetry. Its sensitivity to photons, beta particles, and slow neutrons. The neutron detection is possible due to boron 10, which have a high cross-section for these particles. This material also have linear dose in range ideal for personal dosimetry and clinical applications. Also present low FENI for personal dosimetry and have effective atomic number close to biologic soft tissue. Here you can see two possible applications. In the left side a typical dosimetry and the right side a 2D OSL film. This is the structure of MPO, and here you can see structure parameters and space group. Although these materials present such advantages, there are some points without answer yet in literature. First, TL and OSL mechanism were not deeply discussed. Currently, there are few theoretical works dedicated to electronic structure, but not in defect, dedicated to defect. Some papers have been reported intrinsic emission, but they don't point out which defect is related for. Also, for dopants, it's not clear how they interact with host, if, for example, it's necessary a charge compensation or it's possible substitution in boron site. It's not clear. Then, this work aims to describe the MBO by classical atomistic modeling. This technique is very useful for calculation of defects and to determine which intrinsic defect is the most favorable and clarify which is the most probable substitution mechanism for dopants. Summarizing, we will study defects in this material. The classical atomistic modeling is based on interatomic potentials, where a set of potentials describe interactions between atoms, and their routine is made to obtain the lattice energy to minimization the lattice in material. And here you can see our steps of this modeling. First, we fit a set of potentials to reproduce the material structure and its precursors oxides. A good potential will reproduce a structure with less than 2% and the precursor oxides less than 5%. And the second condition is the formation entropy should be negative to ensure that structure is stable. After this, we use a modulated approach to calculate defects, and a set of solid state reactions give us the most favorable defects. The choice of potential is made based on the bond nature. Here you can see this paper that show magnesium oxygen bonds it's very unique, while the boron oxygen and bonds present some levels of covalent characteristic. And then we choose Buckham potential. It's very typical potential for ionic bonds to describe magnesium and oxygen atoms, and we add three body potentials for boron oxygen interactions. So here we present the Buckham potentials parameters fitted in this working, and here we present the three bodies potentials parameters. I will call your attention for two kinds of three bodies potential. It's happening because boron is organized in two different polyhedron. In the first, in this, here you can see the tetrahedron, and here you can see the threefold the boron organized in threefold coordination. Because we use this model, it was possible to describe the angles more accurately, as I show here. We have a maximum difference 5%. It's yet good for this modeling. So, and we can also reproduce very well the structure, less than 2% for MBO and less than 5% for precursor oxides. We also find formation energy negative. That's confirmed. It's confirmed that all potential is good to reproduce the NBO. So now I will present for you in this next slides the results for intrinsic and extrinsic defects. Before show the results, I need to explain how we got it. Here's a typical reaction for oxygen Frankel. It's an oxygen, and you have a vacuum oxygen plus an interstitial oxygen. So you calculate one defect for vacuum oxygen and another defect for oxygen interstitial. After you use this equation, this initial solution equation, to discover the energy enough to create this defect, and we normalize it by numbers of defects, in this case 2. In the right side you can see one position, interstitial position, and one vacancy position here. And here you can see all equations used for Frankel reactions used, Frankel pseudo shock, and unshocked. We tested all position. It was 4 non-equivalent sites for boron, 1 for magnesium, 7 for oxygens, and 5 interstitial position. The solution ends was normalized by number of defects. So here we present the results. You have almost 500 combinations, but we choose ever for each defect the minimal value, and we can see that the oxygen Frankel is a more favorable defect for the MBO. When we look at in literature, this paper reported an emission in near UV region that could be associated with F-centers. Such a kind of defect is common for insulator materials, and it can be related with defects with frank defects. It's it's possible. This can be also important for TL because the frank defect is important also for TL and OSL mechanism. So, such as we have done for intrinsic defect, we test all possibilities for configuration for dopant substitution in boron and magnesium site. Of course, for case of substitution in magnesium site, a charge compensation is required. Here is the solid reaction used in site defect. We have one reagent on the reagent side, the lanthanide oxide, the magnesium and the boron sites. Magnesium boron sites, and in the product side you have defect is lanthanide in magnesium. The magnesium goes to boron site, and as a consequence you have one boron oxide releasing to surface of materials to infinity in theoretical terms. Here is the energy the solution energy for this, and defects were calculated under boundary condition, that is, this defect was close to this and interacts one with the other, and you have a 5 interstitial position tested, and the solution energies were normalized by number of defects. Here you can see all reactions used in this work with all equations used to calculate solution energy. After calculation, we plotted this graphic is a solution energy versus ionic radius. Only the minimum value for each defect is shown in this graphic, and as a general behavior you can see that solution energy decreasing with increase of ionic radius. We also observe that almost favorable defects can produce an structure with boron oxide deficiency. This can be relevant. This can be useful for production. The lanthanide in boron site is the most favorable defect, and substitution in magnesium is observed for tunnel, erbium, and dysprosium. This result contradicts the affirmation in literature that assigns magnesium sites as more appropriate for impurity. Looking at structures after minimization, you can see the cerium ion complex between two boron chairs in the polyhedron with a C1 point group symmetry. This can explain the useful broadband observed in photoluminescence emission described in this paper. And as a final discussion, you can see the lanthanide creates strain with dislocated boron groups. These groups can be responsible by levels in forbidden band and of material which capture holes when the MBO is under irradiation, as described in this paper. We also know that oxygen vacancy are the most favorable defect in undoped material, as described also in this in this material, in this paper. This paper uses EPR signals to correspond to this defect. Therefore, we think that boron sites and the oxygen vacancy, these defects, intrinsic and extrinsic, should be considered in any luminescence mechanism for magnesium tetraborate. Conclusions. A set potential parameters obtained by fitting obtained by empirical fitting reproduce the magnesium tetraborate and the precursors oxides. The interaction boron-oxygen was satisfied described by three Bode potentials. Results of intrinsic defects predict the oxygen-Frankel defect are the most probable defect in the material for intrinsic defects, and for extrinsic, that isovalent substitution by boron atoms is the most favorable. And the main conclusion is the boron sites play an important aspect in luminescent mechanism, and the next authors should take care with this site. Thank you very much for your attention. I'm open to questions.